Hello, my name is Daniela Diaz Caballero, and for this video, I will be discussing Physics 2212, Lab 3, Magnetic Field of a Bar Magnet. During this video, I will give a brief introduction to the experiment, which will include the purpose of the lab, any assumptions that were made, and the results that were discovered. From there, I would also include the data and observations from the experiment, as well as my computations. Last but not least, I will conclude by discussing theoretical questions that can be inferred by our findings of the experiment. The purpose of this experiment is to measure the distance dependence of the magnetic field due to a small bar magnet and analyze how its distance relates to the magnitude of the magnetic field. To do this, we will be using a bar magnet, a magnetometer app, tape, and a meter stick. Once we calculate our results using our experimental values, we also compare them using the Biot-Savart law. The fundamental principles we covered during this lab was the Biot-Savart law and distance dependence in order to be able to calculate the magnetic field. The result from this experiment was that the distance dependence was negative 3.0073 and the magnetic field dipole value was 2.5445 amp meters squared. Before going into the calculations from the experiment, let's discuss the pre-lab instructions and expectations going in. For Lab 3, I utilized a magnetometer app from my iPhone as a magnetometer to be able to measure the magnetic field due to the permanent dipole magnet. Before starting the experiment, I calibrated the sensor along the magnetic north. To find the distance from the magnet to the magnetometer for the on-axis calculations, I used the BX component. From there, I then found the magnitude of the magnetic field on-axis and off-axis magnetic field and the perpendicular distance d. Last but not least, I want to emphasize the fact that I subtracted B Earth from the measured Y value in the Y direction to compensate for the measurement of the Earth's magnetic field. Now, let's move on to our observations. During the experiment for Lab 3, the following observations were made. The first one was, when the magnetometer was far from the magnet, it would measure the magnetic field close to zero in the X direction. The second observation was, when the magnetometer was moved closer towards the magnet, the X component of the magnetic field that was measured would increase in value. Based on that, we can now show the data that was collected from the magnetometer app. The data from the on-axis magnetic field measurements is found on the right, and the data from the perpendicular axis measurements is found on the bottom. From this data, we were able to calculate the experimental net magnetic field. In addition, if you notice to the left, the graph represents the relationship between the distance and the magnetic field transformed into a line. With this equation of y equals negative 3.0073x minus 14.491, we can move on to our set of calculations. Our set of calculations are seen here. Using the slope of the graph and the distance dependence equation, we can calculate the dipole moment of the magnet. From the equation, we get that n equals the slope, which means that n equals negative 3.0073, and that ln of k equals negative 14.491. From this, we can manipulate the equation of b equals k r to the n to solve for the value of k, which ends up being 5.08 e to the negative 7. Once we know the value of k, we can rearrange the following equation to solve for the magnetic dipole moment mu. In this case, mu equals 2.5445 amps meters squared. In these calculations, we use the distance dependent equation and the Biot-Savart law equation as shown in this slide. Now, we're going to transition and talk about our computation model and code. As you can see, my code shows a function for calculating the magnetic field, which ends up creating the magnetic field due to the dipole in various locations. On the left, you will find the model of the experiment where the blue arrow corresponds for the perpendicular magnetic field, the magenta arrow corresponds for the 45-degree magnetic field, and the orange and red arrows correspond for the on-axis magnetic field. I also calculated the magnetic field at 45 degrees by using the data from the experiment in order to compare them to the experimental values. From this, I got that my distance was 0.25173 and that the magnetic field at 45 degrees is 7.97568 e to the negative 6 for the x component, 2.3927 e to the negative 5 for the y component and 0 for the z component. Last but not least, we will be discussing some theoretical questions that we can infer based on what we learned in this experiment. So the first question is the following. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your result have changed? When using the magnetic north, we can know that the x component is approximately 0, meaning that only one field would be measured. If we did not compensate for this, the x component would not be 0 and the results of the experiment would differ because we would be computing for a different x value of the Earth's magnetic field. Therefore, the values that we would get would be less accurate. The second question is, what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? I would expect the measurements would end up doubling in the amount, but the magnetic field wouldn't change when an additional identical magnet would be added. Last but not least, our conclusion. Based on this experiment, we can conclude that when comparing the computational values to the experimental values, the distances are similar to each other, but the magnetic fields are distinct. From this, we can conclude that the computational model provides a more accurate estimation of what the magnetic field is. Thank you so much for watching, and please do not hesitate to reach out if you have any questions, and I will see you next time for Lab 4. Bye!